Today I'll be talking about massively multilingual shallow fusion with large language models. End-to-end speech recognition models had increased popularity because the end-to-end models are trained on audio text pairs, which is only a fraction of data compared to large amount of text-only data. Therefore, recognizing long tail or rare name entities still remain challenging. There has been many efforts on addressing long tail issues without increasing model size or decoding complexity. One approach is to combine external language models with trains on text-only data. Another approach is to create audio-text pairs from text-only data using text-to-speech systems. The third approach is to use cycle consistency losses. And the fourth approach is to inject text directly into the end-to-end models training. So far, combining external language model is most effective method. The limitations of the previous work on external language model are most of the external language model are relatively small on the orders of 100 million parameters or less, and they mainly focus on monolingual. Recently, there has been huge success with large language models in natural language processing. However, large language models has not been explored in ASR domain. The goal of this study is to explore how large language models can be used in speech recognition tasks. In this section, we present how to combine LLM to end-to-end speech recognition models. To combine external language model with end-to-end speech recognition models during decoding, we use shallow fusion. Shallow fusion refers to log linear interpolation of end-to-end model score and external language model score. In this study, generalist language model, or GLAM, was used as external language model in shallow fusion tasks. The GLAM is a type of LLM which utilized mixture of expert layers to scale up to trillions of parameters. It achieves better performance across 29 NLP tasks than GPT-3, but it is more efficient than GPT-3 due to its sparsity. In this study, GLAM was trained to cover 84 languages without having graduate language information. In other words, we don't tell GLAM what is the language in a sentence, and the computation cost of the GLAM large language model is comparable to 140 million parameters conformer language model, which is much smaller in terms of size. In this section, we evaluate the performance of multilingual GLAM model in shallow fusion tests for 50 languages. Specifically, we compare GLAM to dense language models, such as Conformer. The baseline is a 2 billion parameters end-to-end attention ASR model. First, the author evaluated shallow fusion using English voice search tests and long tail tests, which is called rare proper nouns maps. Let's look at the performance of the dense language model first. In the table on the left, we can see the 140 million parameters conformers or conf 140M reduce the rare word error rate by 3.4% over baseline end-to-end model. Also, the 140 million parameters models does not degrade the English US voice search test, which means it doesn't hallucinate on the general test. Moreover, increasing the conformer language model size from 140 million parameters to 640 million parameters leads to 6% word error rate reduction over baseline. A GLAM models with two experts perform similarly to the conformers 140 million parameters. And increasing the number of experts to 64 or GLAM 64E leads to an extra 4.6% relative rare word error rate reduction. And it also improved the word error rate on voice search general test slightly, 0.1% absolute. Second, we look at the performance on own language. The figure show improvement of GLAM 64E over baseline and other language model. The y-axis show word error rate reduction of GLAM. The more negative, the better it is. The x-axis shows the language. Compared to baseline end-to-end, GLAM improved 86% language with average word error rate reduction 5.5%. The blue bar. In other words, GLAM shallow fusion causes degradation about 2% word error rate degradation for some language. The authors claim the degradation is small without further discussion on the cause behind. Compared to 140 million and 640 million conformers language model, GLAM 64 experts performs better for 82%, the red bar, and 64%, the yellow bars, language respectively. The average relative word error rate reduction are 3.8% and 3% respectively. In conclusion, in this study, authors explore incorporating large language models in large-scale multilingual shallow fusion. Specifically, the authors scale up language coverage to 84 languages. And the authors scale up language model from 140 million parameters dense conformer to 1.9 billion GLAM. The results show that GLAM performs better than dense counterparts, and GLAM's inference computation is similar to 140 million param language model, which is impressive.